Well, this is Paul. I'm shut out of the Science Center, but it takes more than a mere bomb threat to stop Math 116. So let me begin by telling you how to do the variant of the door opener problem where we change the norm. Remember, in the original door opener problem, the idea was that we were trying to minimize the heating in any resistance in the circuit, so we had to minimize the square of the current integrated from 0 to 1. Now what we're trying to do is to avoid tripping the circuit breaker, and so the quantity that we want to minimize is the maximum absolute value of the electric current, which is symbolized by U. So let's first figure out what space to set this problem in. We know of two spaces where maximum absolute value is the norm. One is L infinity, the other is C01. And in accordance with standard practice, we are setting the problem in the dual space X star. Now if X star is L infinity, we know what X is. It's L1. While the dual of L infinity is a pain, the dual of L1 is unambiguously L infinity, so that's going to be our choice. The alternative of using C01 we wouldn't have a clue about. We have not encountered a space whose dual space is C01. Furthermore, we have no reason to believe that the optimal current is a continuous function of time. We're going to find out, in fact, that it isn't. So, now what we have to do is figure out what an element of X looks like. Remember, that's some constant A1 times the first constraint plus some constant A2 times the second constraint. And the constraint functions are exactly the same ones as before. All we've changed are the norms. So our basis functions are e to the t and the constant 1. So the most general function we might want to consider in X is A1 times e to the t plus A2. When we solved the problem in Hilbert space, that turned out to be the solution to the problem. Now all we can say is that the solution is going to be aligned with it, and we need a vector in X, the space big L1, whose norm is equal to 1. What's the norm? Well, it's the integral of the absolute value of the function a sub 1 e to the t plus a2 integrated from 0 to 1, and that has to be less than or equal to 1. That was a practical matter. It will be equal to 1. To finish using Leuenberger's standard recipe, which I have quoted up at the top, we need the constraint values. And you will recall the first constraint says the door comes back to rest. C1 is 0, its final velocity. The second constraint says it opens through an angle of 1 radian. So C2 is equal to 1. That means we have to maximize C1A1 plus C2A2. In other words, we have to maximize A2. So now we have a nice straightforward problem. Let's look at it on the next page. We have to maximize A2, subject to the constraint that this integral is no greater than 1. Now have a look at this function and think about the problem physically. Originally, the current's going to be flowing in the positive direction, the direction that will cause the door to start to open. And so we expect that A2 plus A1 e to the 0 is going to be a positive number. As time passes, this function is going to get smaller and smaller, and we realize that because when we think about the current is going to flow in one direction for a while, then the current is abruptly going to change direction and flow the other way. And if these two functions are aligned with one another, they both have to be positive at the same time. They both have to be negative at the same time. Now what makes this problem solvable is that if we think about a1 e to the t plus a2, this is a monotonic function of t. even if we give these opposite signs, the sum of these two quantities can change sign at most once. It's going to behave like this graph up here. And u of t being aligned with it is also going to change sign precisely once. What about norms? Well, the norm of u to the t is its maximum absolute value, and since the function is always plus or minus some quantity capital M, its norm is M. How are we going to get alignment? To get alignment, we want the effect of the function u in the dual space on a1 y1 plus a2 y2 to equal the product of the norms. And you can see immediately that that's going to be the case, because when we evaluate the function, these terms are both going to be positive simultaneously, or they're both going to be negative simultaneously. U of t will also always have an absolute value of m, and the other factor will be the absolute value of this function value. We integrate it from 0 to 1. So we're going to get alignment. Now let's impose the two constraints. y1 of t is e to the t, and so when we use the constraint and set the value equal to 0, we see that we've got e to the t integrated from 0 to capital T, and aligned with it we have m times e to the t integrated from 0 to the switchover point capital T, and then we have to add on the integral from capital T to 1 of minus m times e to the t dt. So this first integral is e to the capital T minus 1. We subtract off the second one, which gives us an e minus e to the t. That whole business has to be 0. Solving 2e to the t is e plus 1. E to the t is e plus 1 over 2, and t is the natural logarithm of e plus 1 over 2, which my calculator says is equal to 0.62. So we're well underway. We now know that we have to change the direction of the current after 0.62 seconds have passed. All we need now is the maximum value of the current, and we can determine that from the second constraint, using the function y2 of t equals 1. When we integrate 1, we are integrating m from 0 to t, and then we're adding on the integral of minus m from t to 1, and the sum has to equal 1. In other words, mt from the first integral plus minus m times 1 minus t from the second integral, which is equal to 2mt minus m is equal to 1. Solving for m, I see that it's 1 over twice capital T plus 1, and when I plug in 0.62 from the previous part of the problem, I discover that capital M has to equal 4.16 in whatever units Leuenberger is measuring current in, and our problem is solved. I'll put an end to this video now because I'm about to switch to a completely different topic for the next video.